Hi there, everyone. Thank you very much for joining us today for our webinar with Testforce and Signal Monitoring Solutions on signal interference hunting solutions. And thank you for your attention and participation. If you do have any feedback or other webinar topic suggestions for future, then feel free to let me know by chat, or you can email us later at marketing@testforce.com. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you'll be receiving an email afterwards with a copy of the recording. If you have any questions during the webinar, make sure that you ask them in the Q&A section on the right side menu bar, and we'll be sure to get to those questions at the end of the presentation or during the presentation if we have a chance. Today, our panelists are Mark Rasor, President of Signal Monitoring Solutions, Chris Rasor, Vice President of Signal Monitoring Solutions, and Rob Barden from Testforce. Mark and Chris both have extensive backgrounds in the field of spectrum monitoring and geolocation of signals in the military, satellite, and PMR radio communications market, with over 30 years of proven experience in the identification, isolation, and location of a variety of radio signals, including interference. And Rob Barden has over 35 years of experience in the test and measurement industry, focusing primarily on RF technologies. During this webinar, Rob will provide a short overview of the Chasm system that is now available from Signal Monitoring Solutions. And after the overview, Mark and Chris will provide a demonstration of the system using live and stored spectrum data. We also have set aside some time for the participants to submit your questions during the demonstration portion. So you can ask those questions in the chat or the Q&A box. So with that, I will turn this over to Rob Barden.
Thank you. Welcome, everybody. And I'd just like to say thanks again for joining us for this webinar on spectrum monitoring featuring the Chasm solution from Signal Monitoring Solutions. The Chasm system combines software-defined radio technology, SDR technology, with powerful software that provides RF professionals with the tools that you need to monitor and isolate problems that are common in today's radio networks. As I go through this short presentation, you'll notice that the Chasm system software is divided into three primary modules, which we'll discuss here in just a moment. While Mark and Chris do the demonstration, we'll have a short break where they can answer questions, chat questions from you on each of the software modules. So with that, let's go ahead and look at the Chasm system. There we go. Okay. So the Chasm system is designed to help you as spectrum professionals to quickly detect, locate, and isolate interference sources. It's a robust system with the power predominantly in the software aspects of the system. So defending your spectrum, I think you guys all know what we're running into nowadays when it comes to actually managing and defending the spectrum that you're in charge of. Right? The Chasm system is designed to automatically and autonomously monitor RF systems first. That's its primary objective. That's what the system was designed for. As part of that, you can actually cut interference hunting time by up to 90%. You'll be able to see this when Mark and Chris go through the actual demonstration. The system is designed to give you rapid detection of RF spectrum incursions and anomalies. And it uses a type of technology called time difference of arrival, which is TDOA, to geolocate interference sources on a map. It does provide you with the ability to monitor your own narrowband channels continuously, 24/7, as well as broadband monitoring to show signals that potentially walk through your spectrum. I think a lot of you guys might see that where you've got some transient that's coming in or a carrier that's coming in that might not have a good solid reference oscillator, just tends to walk through. The system also gives you the ability to record and play back spectrum, so that gives you evidence from the past of RF intrusions, and that's important. We're going to touch base on that in just a minute here. We also do multi-channel monitoring across a broad geographic regions. We monitor multiple sites from home, office, or field, and the system is rack mountable or portable with battery operations. Okay, let's go ahead and talk about the Chasm software suite. The Chasm software suite really is your defense arsenal to win the spectrum interference battle. It's broken into three systems: the Chasm SPLI, Capture and Overwatch, and the Chasm Geo system. The SPLI is called the Spectrum Viewer Live Instrument Mode, and that provides spectrum and waterfall display in real time or playback mode with GPS timestamp data to easily go back in time and verify any reported interference problems. I'm sure all you guys have gotten issues that have been that come in from your users say, well, 3 in the morning, I had problems on this channel. Now that's great, but most people aren't up at 3 in the morning. So that system gives you the ability to go back in time and look at the interference problems. In addition to the SPLI, we also have the Capture and Overwatch function. The Capture and Overwatch function gives you the ability to monitor all the channels that you want to look at. And pretty much it's unlimited as the number of channels you can look at. So you can monitor each particular channel and then also simultaneously do broadband monitoring. And that's important because as you look at your individual channel, you give that broadband view as well to be able to see what's happening around that channel. Okay. And that gives you a view as that information and the signals are stored into memory for, again, long-term analysis. And this is a great system for doing channel occupancy analysis as well as, of course, interference tracking. And then we get into the Chasm Geo system. The Chasm Geo system is based on multiple receivers that allows you to search and locate interference using the TDOA technology that we talked about. So here's just an example, and Mark and Chris are going to get much more into this in detail when we do the demonstration. But this is the SPLI. As you can see, we've got spectrum view. We have our measurement control parameters on the left, and you can see with the red arrow where the system can actually click on a waterfall or spectrogram going back in time to see what was actually there. The other system, the Capture and Overwatch, this is where we were talking about monitoring your individual channels. So you can see that we've got different channels monitored, but the first box that we have is the wideband monitoring as well. And then we have the Chasm Geo, and this is I got a typo there, I apologize, it should say Geo, but this is where you can actually use the TDOA technology. And you can see over on the left-hand side that we've got 4 receivers that are tracking a particular signal and locating it based on the time difference provided to those 4 different receivers. So that's the software. Let's talk about the hardware real quick. If you're looking for interference hunters and documentation, obviously you're looking for something that can monitor things, but then also give you fast response and from a mobile perspective. So whether it's something you want to take out in the field, something that's dedicated to the network, mounted in an outside weatherproof installation, yes, the Chasm system can do all that. So we have a single unit kit that provides a low-cost platform for SPLI and Capture and Overwatch. That's in a ruggedized case with a built-in directional antenna. Mark will show you more on this in just a minute. And a laptop is included with the system. And then we have multiple receivers, which gives you the ability to mount these in the network. They could still be in the case, which is kind of nice, but tied to the network. So if there is a problem, you can disconnect from the network, take the test system out in the field, and then go find the source of the interference. All these receivers are GPS synchronized. They have to be able to allow us to get to the resolution needed to isolate problems using TDOA. And then you can also see there is a unit case available for outdoor installations, and that can be powered DC, AC, or power removed. So the interesting things that have been done with the system is mounting it on a drone. And this gives you the ability to baseline RF performance anywhere. So you can do pre-installation site surveys of proposed theater locations. take a spectrum review of the environment around the repeater site and at the actual tower height. Survey a tower site without having expensive climbers. That can get expensive compared to using a drone. And then you can hone in quicker on interference sources. And I put in there, even though you have the ability to track this, you can't really do a search and destroy. So anyway, technical support. Our team has over 30 years of experience in the industry supporting land mobile radio, satellite, and military customers with spectrum management. Our only business is to provide spectrum monitoring and geolocation systems using the best available commercial off-the-shelf hardware and software to tailor the complete solution to meet your operational requirements. So, if you have any questions, like I said, we're going to give you a chance to talk during the software discussion points with Mark and Chris. You can put questions in on the chat. In the interim, if you are after the seminar, if you have any questions, call me, contact me on my email. It's right there. So with that, I'm going to go ahead and transfer this over to Mark. I'll give just a second here. And I will now make Mark the presenter. Mark, I think you are ready to go.
All right. Thanks a lot, Rob, for that introduction. Welcome, everybody, to this webinar. I'm now going to demonstrate some of the software that Rob just described to you. Let's start with the hardware, though. So our standard package, it comes like this, easily packs up in a backpack. Open this up. This is has a built-in battery, so it will run for a couple of hours. Matching a laptop. It's got a LAN connection to a laptop, built-in GPS antenna, built-in directional antenna. Even comes with a small second antenna that you can attach, or of course you can attach your own. So it'll run or charge off of AC or 12 volts DC, and all the time, sealed up. This will run outdoors. It's waterproof, as long as it's not in direct sunlight. In a hot climate for a long time. It does need some shade. Otherwise, it can run sealed like this. So I'm going to demonstrate some software now from a live instrument, which is just another an instrument I have over here in the window of my office with an antenna. So we'll be looking at live signals. Give me just a moment to present that. Right. Sorry, I jumped ahead of myself here. Just give me a second. Okay, let's start with the spectrum viewer. So the spectrum viewer, as shown here, is scanning a span. In this case, it happens to be 19 megahertz, but we can stitch together up to 2 gigahertz at a time. So really, it's an unlimited amount of spectrum monitoring. Of course, if you install this in your base station, going through your filters, the same filters that are feeding your receiver, then you'll have limited bandwidth, limited by whatever your filters are. So 19 megahertz typically is going to cover all of that, to cover all the channels that a person is going to look at. So as I mentioned, this is general purpose spectrum monitoring. Think of it as a spectrum analyzer with a time machine. So here I've connected to the database, and everything that we're pulling in off the air here is being recorded in the database, so we can play it back later. Also, you can see the waterfall display here, and we can pause this and go back in time and look at, let's say, for example, this burst here. If that was of interest, we could ask how long did that burst occur? So we simply draw a box around it, and that box indicates that that lasted for approximately 20 seconds. We can jump back in time and look at that burst, or look at a time when that burst was not occurring. So we jump here, and that is that same signal that showed up here. So we can jump back in time like this. Since we're recording, I'll show you in a moment, we can also jump far back in time to anything stored in the database. With this, we can also zoom into signals. So there's some interesting little signals popping on and off over here. So we can simply draw a box around that and see the two markers pop up. And we'll zoom into that chunk of spectrum. The markers I'll show you in a minute serve another purpose. In addition to zooming in, when we get a little closer, we'll use them to measure bandwidth. So here's spectrum and some various signals coming and going. Again, let's zoom into one of these, a couple of them. A little bit closer, get a little bit more resolution. Now we're down to 131 kilohertz. So now we can start to see modulation width and bandwidth. So for example, with markers, I can just press and draw across this and see that that occupies approximately 13 kilohertz, probably a 12.5 kilohertz allocated channel. And you can see these other signals coming and going. Some are on for a long time, some are on briefly. Again, we're recording all this, or if you're just experimenting and don't want to clutter up your database, you can just turn that off and view things live, such that they're not recorded. We are showing what a spectrum analyzer shows right now, so power and bandwidth. But you can see in the signal over here, even from a spectrum analyzer view, we're getting a little bit of a hint as to the modulation type. You can already see that every once in a while that is showing up with no data and just a few spikes. Here, let's pause that, jump back in time and see that. Example of that, come on, where was it? There, forward. There, briefly, you're seeing just these 4 spikes. So that's a clue as to the type of signal. We are pulling INQ data off of the SDR instrument. So theoretically, in the future, theoretically, you can take the INQ data samples and send them to a separate application to determine their modulation type. In the future, that might be something we're adding, but right now we're just looking at frequency and power. When is the signal on, when it's off, and how wide is that signal? What's the bandwidth of that signal? So that's approximately it. You can manipulate this window in various ways. And we covered the markers. Let's disconnect from the live instrument now and go back in time and look at stored data. So let me pick a different channel. And here we are. We can jump back in time again. Now we're looking at recorded data, recently recorded, recorded today at 8 o'clock this morning. And we can step back in time, step forward in time. And we can draw boxes around these little signal bursts and see how long they lasted. That one was some 8 seconds long, and we can click and look at that particular signal is right up here. So like I say, it's a time machine for going back and forth. So far, this is our general purpose spectrum analyzer with a DVR type function for general purpose spectrum monitoring and investigating signals of any kind. Before we jump into the channelized measurements, let's pause here and see if we have any questions that folks would like answered about the general purpose spectrum viewer.
Hi, Mark. Actually, we do have one question that came in. We are wondering, can I access these receivers from the home office or like another remote location?
Excellent question. Yes, in fact, these are Ethernet connected instruments. And yes, they are designed to be operated and accessed remotely. As I mentioned, they could be installed into the base station receiver system off of a splitter tap, just as the receivers are fed and get exactly the same amplified and filtered signals as received at the base station. That is one popular use for these things, but they're portable. So if there's a problem on, say, the transmit side that you would not pick up by being right next to the powerful transmitter with the sensitive receiver, you would take this small receiver and put it in a truck and drive out to some different location away from the strong transmitter and monitor the transmit signals instead. Again, that can be placed on a temporary location like a rooftop connected to a network and accessed from your home, from your office, any network connection, and we'll work with you to help set up your network to get these operating. It does not take a tremendous amount of bandwidth. A modest amount of bandwidth works 200, 400 kilobytes per second would be plenty to operate this network.
So Mark, just this is Rob. So just to recap, basically, if any place, you can put this any place and then monitor it as long as you've got some sort of a internet connection to it, correct?
Exactly, any kind of internet connection. We do it commonly with tethered cell phones or a little USB modem stick.
LTE type modem, you could get
an LTE type modem, and then set up a simple VPN, and everybody can connect to it securely, and it can be isolated from the rest of the networks, and works very nicely. So it can cut down on the commute, especially nowadays when we can't so readily get together, get into the office, and send somebody to drive across town up to a mountaintop. This would be very nice to be able to access it anywhere, anytime. Okay.
Right.
Any more questions?
I don't see any other questions here, Mark, so we can move on to the next section.
That's fine. So this was general purpose spectrum monitoring. Let's put that away for now. Now the portion that is optimized for land mobile radio usage is channelized. So we call this the capture application. And here you input your list of your channels. And I've put some of those based on the frequency that we were just looking at. I picked some of the interesting channels that had signals coming and going, and I put them into this file. We can now run this plan. And this whole utility, we can see that it's ripping through this list of frequencies down here. So it's got 9 bands in it. One of them is the wideband 19 megahertz that we were looking at before. And then the rest are the narrowband 12.5 kilohertz channels with more detail on that particular channel. And it's just racing through this list over and over again until we tell it to stop. We can watch these signals as they come in before they're stored to the database. And watch them in this multi-panel display. So here we have the broadband 19 megahertz wide showing all the channels. So if there was a horrible event like a radar signal stomped in and raised the noise floor 30 dB across the whole band, you would see that here quickly. So you would know that that's not just a problem with one individual channel. But here we see nicely behaved individual channels coming and going. Again, we can put on max hold, min hold, and watch these. One of the interesting ones is this little gas smart meter. So turns out in my neighborhood, we have these smart meters, and they transmit for a whopping 200 milliseconds, about once an hour. So we just rarely ever catch one of these short bursts, usually at low power because it's a transmitter that's a little bit farther away. So that's just kind of a little experiment. These others are regular land mobile radio channels of various bandwidths. So here you can see this one is relatively wide, filling most of the 12.5 kilohertz span. This one is more narrow, perhaps it's allocated at 7.5 or 7.25 kilohertz, something a little bit more narrow. So what we're recording here is the spectrum, both broadband and narrowband, so that can be played back, time stamping it. We're also measuring the occupied, the percentage of time that any channel is occupied above a particular threshold. So in that case, we're measuring the channel power, the total integrated channel power, and recording that in a database table. That allows us to put out a report and a summary and a chart showing for any particular channel, how is that occupancy or power varying throughout the day. That'll help you spot usage patterns. If it's an interfering signal, That'll give you a clue as to when the interferer is on and when it's off. You don't have to just wait for the phone to ring. You now have direct evidence when the interferer is on, when it is off, so you can devise a plan to go hunt an intermittent interferer. So this helps analyze all sorts of things about your radio network. It can be used for noise floor monitoring if an additional filter and preamp is added to the front end. We can get all the way down to the noise floor. But this is a typical use of it right here, not amplified, just straight into the instrument. And it's got plenty of sensitivity, as you can see. So that's our channelized measurement with overwatch and capture.
So Mark, this is Rob. I think one of the things that we can say about the capture and the overwatch is it also gives you the ability to actually do channel occupancy analysis over time. And whether it's your channel or somebody else's channel, it gives you that ability to actually see how often that particular channel is being utilized.
That's true. That's a true statement. So we were, this particular example with this typical setup of 9 channels is using about 4 gigabytes of storage per day. So this can store on a terabyte drive, this can store months of this spectrum data. We can configure the database to wrap around so that you always have the latest amount of data based on however much space you allocate to this recording. Or if you like to archive data forever, that can be done. So we can just pause the system and archive that data off, put in another terabyte disk, and off we go for another few months of recording. That storage rate will increase a bit when we go to the geolocation. It'll increase by perhaps a factor of 5 because we'll be talking to 4 different receivers at the same time, collecting similar sorts of information and storing a little bit of geographic data also. Any questions?
Yeah, we did get one question that came in. One of our listeners is saying that I need to load my own specific frequencies. How do I do that?
Yes, that's easy. So we have a configuration utility to do that. Either loads from a CSV file or directly in the tool itself. So we type that in. So we can configure individual channels. So the channels that we were just looking at came in through here. We can view that spreadsheet. Very simple, you just put in the center frequency, the span, and whatever name you want to give to that channel, or whatever name is meaningful to you. The threshold is used for occupancy measurements if that's of interest. That can be set. So simply import the list of channels, your channels of interest, and then define the broadband that encompasses all of your channels, plus some whatever spectrum you can get through your filter, and add that into this little collection file. And that's what you run. Very simple to use.
Perfect. I didn't have any follow-up questions to that. So.
Okay. Fine. Let's set that aside and look at the third tool, which is geolocation. Now I've been showing you live signals off of live instruments so far. What I'm going to show you now is simulated data. So this is the real GUI, but with simulated data. And here we have 4 receivers defined, and I've allocated colors to them so that we can tell them apart when we get a spectrum trace at the same time from 4 different receivers superimposed. So they're color coded at receiver 4 up through receiver 1. You can see these are set up. This demo scenario is set up to show 4 different power levels received at 4 different receivers. That's typical. And in fact, the time difference of arrival is based on the concept of the same signal arriving a few nanoseconds difference in time at 4 or more receivers. From that information, the computer can extract intersecting curves on the surface of the Earth, indicating where that transmission is coming from. This is an RF measurement, so there's always a little bit of noise and wiggle and so forth. This will not pinpoint such that you can target it with a killer laser beam and obliterate it remotely. This will give you within a block or 2 or 3. But this is far better than, especially when hunting an intermittent signal, far better than taking a Yagi out and spending, I've talked with customers who've literally spent a month or 2 standing out in the field, waving a Yagi around, waiting for that intermittent signal to come up long enough for them to notice that it's up and sweep around in a circle and get an idea what direction that signal is coming from. That, as I'm sure some of you know, is a very time-consuming, difficult, and painful, frustrating process. This is a system that is running automatically all the time on your channels, geolocating signals, whether you ever need to look at their location or not. And then when you have a report that that there was bad interference on a particular channel at some particular time, say 2:30 in the morning, plus or minus 5 minutes, you can go back and play all those back and look at that. So you can see right away roughly where that signal was coming from. So we're going to have a little scenario here where we play through the signals and we show them on a map. And the signal is going to come and go. The scenario is that the signal, I made 2 maps, I'm sorry. The signal is going to come and go from one simulated bad guy talking on a simplex channel. Unfortunately, it's your channel that he's squatting on. Talking from one location, and then he's going to turn off. Now the transmission is gone. So after 3 seconds, that's programmable. The location phosphors out, and then his buddy starts talking from another location, and they just talk back and forth every few seconds in this scenario. And I threw in a little simulated noise so you can get an idea of what a typical location accuracy is. A few buildings or a few blocks, depending on the situation. If you know that that is a fixed, if you strongly suspect that that is a fixed transmitter that's not moving anywhere and it's just one transmitter, you'll be able to draw a box around these dots and say, give me the one averaged center dot that I can show management, because management doesn't like to see a lot of needles wiggling and noise plus and minus and error bars and that sort of stuff that us engineers like to see. I like to see the needle move around, and I know I have a real measurement. But this gives you a very good indication of where that signal originated from. Now you have only a couple of doors to knock on, and you have the evidence to show them when you knock on the door. So when we get here to the signal coming up, you can take a screenshot of that. You can take a screenshot of the map, print it out, put it in an official looking clipboard and go knock on the door. And they'll start by saying, it wasn't me, you didn't see me, you can't prove a thing. And you say, well, sir, you know, it looks like we have the signal recorded here at these exact times, and our location system shows that it's coming from very near your building, and I see you have an antenna, a matching antenna on your roof that looks like perhaps that's where it's coming from. Perhaps we could come inside and investigate, please. So we find that conversation goes much better when you arrive knocking on the door with some evidence other than a vague accusation. So that's our geolocation setup. This is sophisticated technology. It has been used by military and intelligence services for decades, but it required millions and millions of dollars and a clearance, a security clearance to access. today you can get this. What we're doing is bringing this technology to you so that you can use it with a much more modest, much smaller, much more transportable bit of hardware, and really bring this technology to bear on finding solutions to your interference problems. So, any questions on geolocation?
We did have a question that came in. One of our listeners is asking, can my people in the field see this geolocation information as well?
Ah, excellent. Yes, in fact, there's a phone app that we offer. Comes with the system, and it shows the dots on a map to a user in the field. So once a person is driving around out in the field, looking for that last door to knock on, looking for that final antenna on a rooftop that might be full of an aluminum farm, a whole bunch of antennas up there, then yes, that person in the field needs to know roughly where is that signal coming from now. So if it's a mobile signal driving up and down the highway, they need to know where that signal is coming from so they can get ahead of it and watch it drive by. And they need to know when it's on and when it's off. And so the simple little phone app will show them that.
Okay, and then earlier we did get a question as well that was asking how many receivers are needed to pick up the interfering signal?
4. 4 is the answer. So the math works out such that 4 is really the minimum needed. 4 receivers receiving the same signal at the same time. So 4 mountaintops that are all picking up the same signal at the same time, or more. As the network grows, adding more and more receivers, of course, gives you better and better coverage. So I don't want to oversell this, oversell TDOA technology. It has a limitation in that CW signals, unmodulated signals, have no time difference. And so mathematically, they cannot be located by a time difference of arrival system. If they're pulsed on and off, then that is actually a modulation. And that will work. We can find those, such as radar pulse signals, CW pulse signals. But a pure CW signal, the information you get is the relative signal strength at the different locations, at the different receivers. And from that, we'll provide a rough estimate based on RSSI, based on the assumption that the transmitter is an omnidirectional antenna. So even with a CW signal, you'll have some indication of where the signal is coming from.
Okay, thank you. And this next question, it goes back to when you were talking about multipath. So we're wondering, how does multipath and clutter impact the measurements?
Just like any RF measurement, multipath and clutter certainly impact the accuracy of such a system. Some of you may have worked with angle of arrival or direction finding systems in the past. Chris and I have worked extensively with those, put them out in the field for some military, other government customers, and these large, expensive DF antennas will give a nice bearing towards a signal. A second one will give another bearing from another location where those bearings cross. That's where the transmitter is. And that's wonderful in an open area. When there is clutter and multipath reflections and blockages, DF systems quickly run into trouble. They quickly develop large errors if they give an answer at all. TDOA is more resistant to that and will still give a usable answer even in the face of some significant multipath clutter and blockages.
Okay, and we have another question regarding the receivers. So besides batteries, how are the receivers powered?
Excellent question. So It'll run off of 12 volts DC, comes with a cigarette lighter adapter. Switch.
Mark, this is Rob. Can you actually switch your screen to your camera view so that they can get a better picture on that? There we go.
Okay, so it comes with a 12 volt DC adapter, so you can plug it in and run it that way off of a vehicle, or an AC adapter, so you can just plug it into a fixed location and run indefinitely. So it's easy to power. When we put it on a drone, we just power it from a small drill battery or a LiPo battery.
Hey, Mark, can you show the side connectors real quick so they can get a feel for the interconnect and how it's set up?
So when you use that, here's the Ethernet connector. Let's see. I can get enough light on that. Let's see. So there's an Ethernet connector, and then we have a separate waterproof power connector here, where you can plug in either the AC or the DC adapter. And then on the other side, we have an auxiliary N-type connector for your antenna, or for the little auxiliary antenna that comes with it. Or you can use the built-in directional antenna. So this is a full kit and will work for TDOA or just spectrum monitoring. This can be useful for your final door-to-door search or antenna-to-antenna search, just pointing the directional antenna at the various antennas until one of them peaks in power, and obviously that's the one. Any other questions about any of these Chasm tools from Spectrum Monitoring Solutions?
We do have another question. One of our listeners is wondering if this system covers the VHF band, 138 to 174 megahertz.
Absolutely. In fact, the receiver covers from 70 megahertz up through 6 gigahertz. If you need to go above 6 gigahertz, we have other receiver models that we put in and use the same software, and we can take you up to 40 or 50 gigahertz these days. Seems like every month somebody comes out with another more wonderful high-end, high-frequency receiver for the 5G frequencies.
So a follow-up from our listener is, would you need to have an external Yagi antenna?
You certainly can.
Maybe mispronouncing.
No, that's right. Yes, absolutely. You can hook a Yagi antenna up to this outdoor port. This internal antenna is directional from about 650 megahertz and up. So of course that's not going to be directional at VHF. You'd want to put some other kind of directional antenna on that for those lower frequencies. And so that's the idea of the external port. You can put your own antenna on that's appropriate for your purpose.
Okay, thank you. So far we're up to date with the questions, but if any of our attendees have any other questions, feel free to enter those into the Q&A or chat section and we will get to those. If any questions do come up later that you think of, then you can send any of our panelists an email. Their contact information, Rob's contact information was on one of the previous slides, or you can just reply to me, to Rebecca's email, and I will put you in touch with the right person.
All right, well, thank you very much, everybody. Look forward to meeting each of you in person one day when we can move about the country again, or in video chat before that.
All right, that's great. Thank you so much for your time today, to Rob and Mark and Chris for being on the line. That was great. I think it was very interactive, and thanks to everyone for the questions that you asked throughout. And if you do have any other questions, feel free to send us an email. An easy email address is marketing@testforce.com, and I will get you in touch with the right person. And if you have any other suggestions for webinar topics in the future, you can also include those too. We love to hear your feedback. So we've come to the end of the session today, and I hope that everyone has a great day. Stay safe, and thanks again, everybody.